Hello, my name is Melissa McReynolds and I'm the Vice President of Technology Development for Sentient Science. I'm going to talk to you today about our software technology, DigitalClone for additive manufacturing. It can predict the material microstructure and fatigue life for additively manufactured components. Sentient's core technology, DigitalClone, includes a microstructure-based approach for simulating the fatigue life of a component. DigitalClone is a physics-based modeling tool that simulates the microstructure of different components and their behavior. It calculates internal stresses caused by different applied loading conditions, accumulates internal damages resulting in crack nucleation and propagation, and investigates the performance and life prediction of the parts. This same methodology and software technology can be applied to the emerging market for additive manufacturing. Digital Clone for additive manufacturing provides similar capabilities as our Digital Clone for engineering product, but it is capable of predicting the material microstructure and fatigue life for components built using various AM processes. Our software for additive manufacturing can help solve the problems experienced by design and manufacturing teams. It can model to determine the optimal machine settings or parameters to obtain the desired porosity level and eliminate defects in the build process. As you know, the AM industry has many challenges that need to be overcome to make it a viable production solution. Manufacturers are making huge investments in additive machines, engineers, and designers. But there's also a desire to print parts using materials that are not typically 3D printed. There's some gaps there, though, that have issues centered around obtaining a successful build. Verifying functional performance that meets end use requirements before deploying AM components into the field is critical. Conventional destructive testing methods provide limited data at high costs. The main challenge in analyzing components built through AM processes is consideration of their specific material microstructure and how it affects the performance and life analysis. Conventional FEM approaches do not consider these effects. These are some quotes from industry leaders that are representative of some challenges the AM industry is seeing. The inability to predict residual stress, the part to part variation, and not being able to know if a part is going to print and live are some of the unsolved reasons AM is not widely used in manufacturing. We think we have a solution to help with several of these known challenges. We've been awarded over $6 million in the last 6 years from multiple government agencies to expand our technology and apply it to additive manufacturing. Our start was with the Department of Energy. We had a program where we simulated the material microstructure of an additively produced part to determine the fatigue life. We worked with the Navy to optimize the designs of additively manufactured parts for both reliability and inspectability. We have an Army program that focuses on in situ inspection of additively manufactured parts, and we've done programs that focus on specific aluminum alloys. Most recently and currently, we're working on a program with NASA to enhance our technology to develop models that will predict geometrical accuracy and microstructure in metal AM. From all of this R&D, we have generated two products. Digital clone for additive manufacturing shown on the left, which I will discuss in detail throughout this presentation, and digital clone for in situ monitoring and defect correction, which is a result of our Army program. DCIM, through a closed loop feedback system, will detect defects during the build process. Models will be run during the build to determine when or if a repair is necessary to maintain the desired life and performance of the part. It is considered to be an in-process quality improvement tool that will increase the repeatability of additively manufactured parts, improving their reliability to meet qualification standards. Like I said, our models can be used to find defects during the build process, and then we can take that one step further and use our models to determine if those defects will cause an impact on the life of the component. If the defect will negatively impact the life, then using a hybrid AM machine, a repair can be performed during the build process. This closed loop feedback leads to reduced failures of parts at the end of the printing process, fewer prototypes required, and results in parts that last for the desired or specified life. Now let's get into some of the details of our DCAM product. To predict the life for a part and see if it's a qualified recipe, there are 3 steps in our AM platform: process, microstructure, and fatigue. In the process module, we simulate the part level distortion and residual stress with respect to various key process parameters. Then we simulate the microstructure, that is the grain structure and porosity of an AM component with respect to key parameters and locations of interest. And third, we simulate the fatigue performance of the AM components at specific mechanical loading conditions. This physics-based simulation suite has been well demonstrated in different AM platforms. For example, powder bed fusion and direct energy deposition, and several alloy systems that our customers have been interested in. Those materials include, but are not limited to, Inconel 625, Inconel 718, a couple different stainless steels 17.4 and 15.5, as well as titanium 64. Additionally, the simulation suite can be applied to any new alloy with minimum calibration needed. This physics-based simulation suite directly benefits the user because it allows computational testing for new component design, new materials, and new processes, which will significantly reduce cost and time compared to the conventional physical testing. The process modeling is the first step in Sentient simulation framework. It involves a physics-based multi-scale model that considers different time and length scales. Specifically, the model takes several key inputs, including process parameters like power, scan speed, laser thickness, hatch space, and material properties, and simulates the temperature evolution at a microscale level. We start with the parameters that are set on the AM machine. Then we simulate the AM process. We insert layer by layer of powder, pass the laser, simulate the change in the state of the material. The output is residual stress and distortion that would be left at the end of the build, and the thermal history for every point in the part during the build process. On the left, you can see as the laser passes over the part, and then also a comparison between our simulation and NIST experimental data. On the right is a screenshot of our software in the process module. Microstructure is the second step. Now that we have all the thermal information, a thermal model is run using 3D FEA to calculate the temperature evolution within the AM build process. We use this thermal distribution to predict the microstructure which is created during the build and comes out of the machine for those specific parameters set on the machine. The predicted temperature history is correlated to pore formation to calculate the porosity of the build. The heat flux model can be customized to fit different heat sources. As such, Sentient's model can predict accurate melt pool dimensions, which can be correlated with lack of fusion porosity. And the model correlates keyhole boiling porosity with melt pool areas when temperatures are above material boiling temperature. Third, in the performance modeling, now that we have the microstructure, how will cracks initiate and propagate, and what will be the life and impact to the life of the part? The ultimate goal is to make sure that the additively manufactured part will satisfy the performance requirements. Starting with the part and its load analysis, we add in the microstructure, apply a load, and run the model to see how the crack would start and propagate until failure. This builds the SN fatigue dataset computationally without having to build and test each part physically. This would save a lot of money and time. Let's take a look at a quick demonstration of DigitalClone for additive manufacturing, narrated by our Vice President of Product Development, Andrew Veckart. You will see the 3 modules I've explained and the outputs you can obtain through the use of this software.
This is an overview of Sentient's DigitalClone for Additive Manufacturing Software, or DCAM. DCAM allows users to simulate different types of metal additive manufacturing processes to predict part residual stresses, distortion, and microstructure. DCAM also includes Sentient's proprietary component life prediction technology to leverage these simulation results for prediction of component reliability and fatigue. DCAM implements a workflow around projects, wherein many different analyses can be applied to a part. An analysis joins a part with a machine, material, and collection of process settings. Users can extend the material and process settings library. DCAM currently supports custom material specifications for titanium alloys, nickel alloys, and steels. Custom print settings may be created for a variety of laser powder bed fusion and directed energy deposition machines. The process simulation module is used to predict the residual stress and distortion of parts built with additive manufacturing. Results are available both before and after the part is removed from the build plate. Users can view the predicted displacement vector and stress and strain tensor components. The microstructure simulation module is next. Here, a user can specify the volume of material for which to predict the microstructure. They can also choose on which planes the microstructure should be predicted. There is randomness in these predictions. Therefore, a user can choose how many different microstructure samples to produce to capture this randomness. In post-processing, the user is able to see the grain size distribution on each of the planes for which a simulation was requested. Furthermore, for each individual microstructure, a user can see the grain size histogram, as well as a plot of the grain morphology. The grain morphology plot is furthermore interactive, so the user can explore and experiment with the microstructure. Finally, in the fatigue simulation module, the user is able to select one or more of the predicted microstructures to use for virtual fatigue testing. Material cleanliness and porosity are directly specifiable, and the simulation runs on larger servers on AWS to produce results efficiently. In post-processing, a user is able to view the computed failure times on an SN curve plot. At each load level, a user is further able to conduct and visualize a Weibull analysis. Finally, animations of the initiating and growing crack are available in the software as well. These are the primary features of DigitalClone for additive manufacturing.
So in summary, whether or not an additively manufactured part will live or crack or distort because of thermal stresses is an unknown. Our software models can be used to evaluate what will occur when the support structure is removed from the printed part, or how much of a life impact certain heat treatments or surface finishes will have on the part. Again, DigitalClone can be used to reduce the trial and error of the builds and post-processing by computationally modeling the effects of the same. There are a wide variety of machine settings that can be changed to optimize the print and get a successful print. Without simulation software, this would require multiple coupon runs anytime a setting or a material is changed. DigitalClone for additive manufacturing can be used to reduce these trials and qualify a recipe for a specific material and machine at less cost and in less time. And then to take it one step further, knowing if it's feasible to print a part is one thing, but knowing whether the printed part will meet the design life as specified is ideal and valuable, right? So starting the printing process without knowing the answers to some of these questions leads to higher costs and wasted machine time due to a large amount of failed parts out of the build process. Being able to computationally model the design and run the simulation for lifing will lead to more successful builds at lower cost. And that's our goal. So, what are your challenges and roadblocks for additive manufacturing? We're interested in hearing about them. Are you having to print multiple coupon samples every time you change a machine setting or a material recipe? Are you seeing a lot of cracking or distorting in your parts after they're printed? Are you struggling to figure out how the life of a part will be impacted when the support structure is removed or when you post-process the part? Contact us with your biggest concerns, and we would be happy to set up some time to dive deeper into our technology and address your issues. And now I believe there's some time for Q&A.